In the last session, we were talking about a couple of details related to the design of foundations or design principles of foundations, you can say. So from today's class onwards, what we are going to do is we are going to look after how to do the manual design of foundations, or you can say manual design of footings. So in this part, we are going to discuss about five different manual designs of footings. So the starting with the first one that we are going to discuss in this particular session is design of isolated rectangular footing. So this is what that we are going to see in this particular session. So after that, we will see the square footing, the combined footing, strap footing, and other types of footings, whatever that are there. Right. So in this session, we'll be discussing about the design of isolated rectangular footing. So before discussing about the design process, let me show you the problem statement. So for what condition we are going to design the rectangular footing, and then we'll proceed to the design process. So the first problem statement for this particular thing is, so you can see the question here, a solid footing has to transfer a dead load of 1200 kilonewtons and an imposed load of 300 kilonewtons from a column of size 230 by 450 mm. So this is the column size, and these are the loads that are coming onto the member. Okay, and the grade of concrete which is used is M20 grade of concrete, and the grade of steel is Fe415, and the safe bearing capacity of the soil is found to be 300 kilonewtons per square meter. So now what we are going to do is we are going to design a footing. Okay. So now before designing the footing, it is always important to understand what should be the maximum settlement in any type of footing, not just in isolated footing. In general, what does IS code tells is whenever you design a foundation, the maximum settlement in any kind of foundation is assumed to be 25 mm. That's the maximum allowable settlement. More than that, it is not allowed, because if the settlement goes beyond 25 mm, then obviously the column member or the entire footing or the foundation itself will get failed. So for that reason, in general scenarios, we will do the assumption of allowable settlement as 25 mm. That means it's a maximum settlement that should experience by the footing. Okay, right. So now in the first step, what we have to do is first we have to decide what type of footing we have to do. So isolated footing, it's fine, but what shape? So should it be a square footing? Should it be a rectangular footing? Or should it be a circular footing or a trapezoidal footing? Which shape? That's the most important thing. So usually the general thumb rule while designing the foundations or while designing the footings is for a square column. Okay, whenever you have a square column, it is always suggested to go with the square footing. Okay, for square column, square footing is done. And then for a rectangular footing is prepared. Yeah, this is the blind thumb rule. Sometimes this thing may not be true in all the cases, but in most of the cases, especially in the real-time scenarios, people follows in this way only. If it is a square column, then we'll obviously decide the square footing. If it is a rectangular column, then we will design the rectangular footing. So here in our question, we have the column size as 230 by 450 mm. That means it's a rectangular column. So since it's a rectangular column, we are going to design the rectangular footing. Okay, since it's a rectangular column, we are going to design the rectangular footing. That's the scenario here. Now, so in the first step, what we have to find is we have to find the in-plan dimensions of the footing. Okay, we have to find the in-plan dimensions of the footing. So what is this in-plan dimensions? So this step 1, step 2 does not necessarily indicate exactly the step 1s and step 1, 2, 3 like that, but I'm just giving it in 1, 2, 3 like that. Okay, just for our better understanding. Right. So in the first step, we have to find the in-plan dimensions of the footing. So what is this in-plan dimensions? So in-plan dimensions of the footing is nothing but length and width of the footing. Okay, for every footing we have the length and we also have the width and we also have the depth of the footing. Depth we will find out after some time. But first let us focus on the in-plan dimensions of the footing. So in-plan dimensions are nothing but the length and width of the footing. Okay, the length and width of the footing are called as in-plan dimensions of the footing. Now, how this length and width of the foundation can be determined? So the length and width of the footings depends on two important things. Okay, the length, or you can say the L and B, that is length and width of footing depends on two parameters. The first parameter is known as the load coming from the column. The load coming from the column is the first parameter, and the second parameter is the SBC of soil. These are the two things which are required in order to determine the in-plan dimensions of the footing. So how will we find out? So we have the formula which is area equals to load by SBC of soil. Okay, load upon SBC of soil. Now here we have the SBC of soil that is given in the question, which is 300 kilonewtons per square meter. Now we need to find out the value of load. Okay, we need to find out the value of load. Now, if you observe here, we have two types of loads that a footing will experience. What are those two types of loads? The first one is called as a dead load, and the second one is called as imposed load. You can also call this imposed load as a live load as well. So we have the dead load and we have the live load that is coming onto the structure, or that is coming onto the footing. So therefore, total load equals to, so dead load plus imposed load. You can also call it as a live load. So I'll just make it as IL, which represents imposed load. So what is the dead load that is coming onto the structure? It is 1200 kilonewtons plus what is the imposed load? It is 300 kilonewtons. So therefore, the total load that is coming onto the member is 1500 kilonewtons. So we don't need to work with the factored load and all. As of now, it's not required, especially when you are finding the in-plan dimensions. It's not required currently to go with the factored load. Okay, so right. So this is the total load that is coming onto the structure. This is first scenario. Okay, the load factor we are discussing here. Okay, SBC is fine. We are going to determine the load value. But again, this is not the final load. Okay, this is the total load that is coming onto the footing. But the second important thing that we need to understand here is, so the second important thing that we need to understand here is how much amount of load, or what is the self weight of footing. Okay, you can call it as self weight of footing. So this is the total load that is coming onto the footing. But when you construct any structural element, it will have its own self weight. Okay, it will have its own self weight. Similarly, since we are constructing the footing, footing will also have the self weight. So how much self weight of the footing we need to find out? So here we don't know. Suppose, let's say, if you want to find out the self weight of footing, we should know the length of the footing, the width of the footing, the depth of the footing or the foundation, and then all these three has to be multiplied with unit weight of concrete. Okay, when you multiply all these three things, that is length into width into depth into unit weight of concrete, then you are going to get the self weight of footing. This is how usually we get. But currently, unit weight of concrete is fine because it's considered as 25. But length, width, and depth of the footings are unknowns here. So since these three parameters are unknowns, what we are going to decide in general is the self weight of footing. Okay, the self weight of footing is taken as, okay, is taken as 10% of load coming from the column. 10% of load coming from the column. So what does it mean? It means whatever the load that is coming onto the column, or that is coming from the column, that is an addition of dead load and live load, which is 1500 kilonewtons. In this 1500 kilonewtons, 10% of this 1500 kilonewtons will be the self weight of footing. Okay, 10% of this 1500 kilonewtons will be the self weight of footing. So therefore, self weight of a footing equals to, okay, self weight of footing equals to 10% of the total load. What is the total load? Total load is 1500 kilonewtons. So therefore, it will become 150 kilonewtons. Okay, this is 150 kilonewtons. So now, how much load that is coming onto the soil now? So this is 1500 kilonewtons is the dead load and live load combination, and footing is also having some self weight, which is considered as 10% of column load, that is 150 kilonewtons. So on a whole, the total load transferred to the soil, okay, therefore the total load transferred, okay, the total load transferred to the soil equals to, what's the total load? So the 1500 kilonewtons, which is a combination of dead load and live load, plus from self weight of the footing, which is 150 kilonewtons. So that equals to 1650 kilonewtons. So this is the total load that is coming onto the soil. Remember, we are not designing the footing to take the load. It is meant to transfer the load. So that is why I'm writing here total load transferred to the soil. Okay, so it is not total load bearing by the column, or it is not total load bearing by the foundation, nothing. It's a transferred load. Okay, so therefore, for this load, we have to find out the length and width of the footing. So we have the formula, which is area equals to load by SBC of soil. We have the load value, which is 1650 kilonewtons, and we have the SBC of the soil as well, which is 300 kilonewtons per square meter. So from this, we can find out the area of a footing. So area equals to 1650 divided by 300, which is SBC of soil that is given in the question. So when you solve this one, the value of area will become 5.5 square meter. 5.5 square meter. So this is the required area of a footing. You can call it as required area of footing. So this is how you're going to find out the area of footing. Now here one thing which we have to remember is we have found out only the area of footing. Okay, we didn't find out the dimensions. We found out the area of footing. So now we have the area of footing. So how to decide the sizes of the footing based on this area? Okay, how to decide the sizes of the footing based on this area? So that's our important thing here. Right. So how to decide the sizes of footing based on area? So here the length and width of the footing has to be decided in such a way that the pressure distribution should be uniform. Okay, this is the most important thing. Usually when you are doing in the classrooms or when you are following any RCC concepts, you will be doing this one, but you don't understand what is the real scenario behind it. So the length and width of footing should be decided. Okay, the length and width of the footing should be decided such that, okay, such that the pressure distribution, okay, the pressure distribution should be uniform. Okay, the pressure distribution should be uniform at the base of footing. Okay, at the base of the footing. So whatever the footing that you're going to construct, at the base of footing, the pressure distribution must be uniform. Let me show you one particular diagram here. Right. So if you observe this particular figure, let me give this one just a second. Right. So if you take this particular figure, which is this one, let me paste it here. Yeah. So if you take this particular figure, it's very clear from this figure that, so the pressure distribution. So how the pressure distribution should happen? So the pressure distribution should be uniform such a way that whatever the pressure that comes from the column or whatever the pressure that comes from the top of the foundation, it should be distributed uniformly. So how will you ensure the uniform pressure distribution? Okay, how will we ensure the uniform pressure distribution? So in order to ensure the uniform pressure distribution, whatever the sides that you take, suppose this is the column, okay, this gray color one is the column and the black one, black outline is the footing. So from top view, you can say this is a plan view. So once you arrange the column in the footing, okay, in the rectangular footing, once you arrange a column, let it be a rectangular column only, from any side, whatever side you take, the sides should have the uniform dimension. Okay, the site should have uniform dimensions. So to ensure the uniform pressure distribution at base of footing, okay, to ensure uniform pressure distribution at base of footing, the value of x, here the x is called as the projection. Okay, x is called as projection. So the value of projection, that is x value, should be same on all sides of column. This is the important thing, especially when you're going with the uh, I mean, the software design, CSI safe software design, these things are very much important. Okay, right. So to ensure, so let me write that one. So to ensure the uniform pressure distribution, have I written that? Yeah. So to ensure the uniform pressure distribution, to ensure the uniform pressure distribution at the base of footing, where at the base of footing. So the projection, okay, the projection, basically it is x value. In this case, I'm just considering it as x. So the projection on all sides of column, okay, the projection on all sides of column should be same. It should be same. So this is what we are going to decide the dimensions of the footing on this scenario. Now, here the condition is we have two types of positioning of columns. One is called as two types of positioning of columns. So one is called as centrally positioned column. One is called as centrally positioned column, and the second one is called as eccentrically positioned column. Okay, or eccentrically positioned columns. Okay, eccentrically positioned columns and centrally positioned columns. So what is this? What is this meant by centrally positioned column and eccentrically positioned column? Centrally positioned column is nothing but, let me draw a simple figure here. Right. So this is the base of the foundation. Okay, this is the base of the foundation. Let me call this as the base. And on the top of the base of the foundation slab, we have the column. If you provide the column, okay, or if the column is provided exactly at the center of the foundation slab, okay, exactly at the center of the foundation slab, such kind of columns are called as centrally positioned columns. Okay, such kind of columns are called as centrally positioned columns. Eccentrically positioned columns are nothing but, now in the centrally positioned columns, what will happen? The pressure distribution will be uniform. Whatever the load that is coming from this column, it will get transferred to the foundation slab, and this foundation slab will distribute the pressure uniformly to the soil base. Underneath this, you have the soil base. So whatever the load that is coming from the column and then transferred to the foundation slab, this load which is coming from the foundation slab will be uniformly distributed to the subsoil. That's called as centrally positioned column. That's the scenario with centrally positioned column. So what is the scenario here? In centrally positioned columns, the load distribution or the pressure distribution will be uniform. Okay, the pressure distribution will be uniform. And whereas in eccentrically positioned column, suppose let's say I'm going to place the column like this. Okay, this is an eccentrically, it is not exactly placed at the center of the foundation slab. At some distance of x, I have provided the column. Now what will happen here? More amount of pressure will be there along this sides. Okay, along the left side of the foundation slab, more amount of pressure will be there. And when you go towards the right end, you don't have the uniform pressure distribution. So it will be basically an uniformly varying load. So here you will get huge amount of loads. Let me show you that one. Right. So here you will get more amount of loads because the column load will get distributed in that way. But when you move to the other end, the intensity of load will get reduced. Okay, the intensity of load will get reduced. So here what is happening? More amount of load is falling on one side of the footing or the foundation slab, and less amount of load is falling or is coming onto the right side of the foundation slab. Now, when this is the scenario, what will happen? More amount of load is being experienced here. That means the column will push this foundation towards this side. And then this part of the foundation slab, the right side portion of the foundation slab, will experience an uplift condition. Okay, this portion of the foundation slab will experience an uplift condition. So to avoid this uplift condition, it is important to position the column exactly at the center. So that is the reason why I was telling that to ensure uniform pressure distribution, the column has to be placed exactly from a distance of x from all sides of the footings. When you don't satisfy this condition, then obviously the footing will experience, or the foundation slab will experience, the uplift condition. So we already talked settlement is okay, but uplift is never an okay. Okay, PT less than S, PT greater than S, that we have discussed in the last session. So when the column is positioned centrally on the footing, the uniform pressure distribution will happen, whereas the settlement will also be uniform. Okay, settlement will also be uniform. But when the column is positioned eccentrically on the footing will have more pressure distribution on the one side and less pressure distribution on the other side. Because of this uneven pressure distribution, settlement will happen, and this settlement is very dangerous. Why? Because it will be an non-uniform settlement, or unequal settlement will be experienced. Equal settlement is always good, but unequal settlement is never a good option. Right. So that's where we are going to decide the dimensions of the footings. Right. So now we have the area of the footing, which is 5.5 square meters. Okay, this is the area of footing, which is 5.5 square meters. So how will you define area? Length of the footing into width of the footing. That is called as, the length and width of the footing is called as area. So that is a 5.5. Okay, we have got the length of the footing. I'm just representing with LF. Width of the footing I'm representing with B suffix F. So let us consider this as equation 1. So I'll just call this one as equation 1. Right. So now from this we have to find out the values of LF and BF. So how will we find out? Suppose if you observe the figure, okay, LF equals to, if you observe this particular figure which is provided here, so I'm considering this as the length of the footing and this as the width of the footing. Okay, this is length of the footing and this is width of the footing. I hope it is clear for you. Right. So how will you define the length of the footing? Length of the footing is defined as x. Okay, this side is 1x and here it is another x. That means x plus x is 2x, and this side of the footing. Okay, this side of footing. So what I'll do is I'll call this side of the footing as A. Okay, the longest side of the footing as A, and the shortest side of the footing, sorry, the longest side of column as A, and the shortest side of the column as B. So therefore, x plus this length, which is called as A plus x. That means A plus 2x. Okay, A plus 2x. That is the length of the footing. I hope it is clear. If anybody is having doubt, you can please unmute and ask the doubt. Right. A plus 2x. That's how we are going to get the length of the footing. Similarly, the width of the footing. Okay, width of the footing, how we will get? So width of the footing is, so this side it is x. Okay, this side it is x, and this side also it is x, which is 2x. And I'm considering this side of the column. Okay, this side of the column as b. So x plus b plus x. That means b plus 2x. So that's how you're going to get the values of length of footing and width of footing. A plus 2x and b plus 2x will become the length and width of the footing. Okay, length and width of the footing. So now we know the LF value and BF value. We just have to substitute that. So LF value is A plus 2x. Let me write that. A plus 2x plus, sorry, into BF value is B plus 2x. Okay, B plus 2x equals to the total area. What is the area of footing? It is 5.5. So from this, if you solve this one, so we know the value of A. What is the value of A? This one, this side of the column. So what is the value of A? We have the dimensions of the column, which is 230 by 450. This will become B and this will become A. So okay, the larger dimension will become A, the smallest dimension will become B. So for your convenience, I'll just write that one. So here A equals to 450. Okay, A equals to 450, B equals to 230 mm. These are the dimensions of the columns. Remember, don't think anything else. It's there 450 and 230 mm are the dimensions of the columns. Right. So we have the values. Let's say the value of A is 450. So I'll just convert into meters. So 0.45 plus 2 times of x into B, which is B is 0.23 plus 2 times of x, that equals to 5.5. So if you solve this one, you will get a quadratic equation in terms of x square plus 2x or ax square plus bx plus c. That's how you're going to get. So once you solve that quadratic equation, you're going to get the value of x, which is equals to 1. Okay, you just have to substitute, you just have to solve this equation. Okay, once you solve this equation, you will get the value of x, which is equals to 1. So therefore, what should be the value of x from all the sides? It is 1 meter. So the projection on all sides of the columns. So this one represents, therefore, okay, therefore, the projection on all sides of column. Okay, the projection on all sides of column x equals to 1 meter. So this means you have to maintain 1 meter distance around the column. Okay, that should be the exactly positioned, which is at a centrally positioned column instead of eccentrically positioned column. So this is how you are going to find out how to decide the dimension of the column or the size of the column on all the sides, which is 1 meter, the value of x. That's called as projection. So now we got the value of x, which is 1 meter. Now from this, can we find out the value of length of footing and width of the footing? Yes, we can find out. Why? Because we know the value of A, we also know the value of B, and we also know the value of X, which is projection, that is 1 meter. So just substitute the values of A, B, and X in LF and BF values or LF and BF equations. You will be ending up with the length of the footing and width of the footing. So what is A? A is 0.45. I'm just solving this one, A plus 2x. The value of A is 0.45 plus 2 times of x. X value is 1. So 2 into 1, that equals to 2.45 meters. Okay, 2.45 meters. Similarly, BF also we have to find, that is width of the footing. So how will you find out width of the footing? B plus 2x. Okay, B plus 2x. What is the value of B? The value of B is 0.23 plus 2 times of 1. Okay, 2 times of 1. So therefore, the value of B will become 2.23 meters. Okay, 2.23 meters. Now, if you provide these dimensions to the footing, then uniform pressure distribution will happen. But in real-time scenarios, you cannot exactly provide 2.23 meters or 2.45 meters. So what we have to do is we have to round off these values. If you remember, in the last session, I was highlighting about these dimensions only. So to have the uniform pressure distribution, you should not directly adopt the as it is dimensions that you are going to get. So what you have to do is you have to round off these values. So what will happen when you round off these values? More amount of uniform pressure distribution will happen. Okay, so right. So I'm just considering 2.45 meters. So I'm just rounding out it off to 2.5 meters and 2.23 meters. I'm just rounding off to 2.25 meters. Okay, so you should not go much greater than whatever the values that you're getting here. Just be around that value with a approximation value. Okay, with the nearest possible approximation value. So this is how we can decide the length and width of the footing. Now we have to check. So this is the provided area. Okay, what is that? The provided area is, or the required area is 5.5 square meters. Now, how much we have provided? That gets changed. So provided area of footing. Okay, provided area of footing equals to, provided area of footing equals to 2.5 into 2.25. This is the provided area. So 2.5 into 2.25 will give you 5.63 square meters. So 5.63 square meters is greater than the required area, which is 5.5 square meters. So therefore, whatever the area that we have provided to this footing, it is in the safe condition. So therefore, there is no problem. So that's how we have to decide the sizes of the footing, that is length and width of the footing. Okay, I hope it is clear how to decide the length and width of the footing. Right. Now, the next thing that we have to discuss is the upward soil pressure. Okay, upward soil pressure. So up to here, if anybody is having any doubts, you can unmute and ask. Any doubts for anybody up to here? If you don't have doubts, then I'll proceed further. So I'll consider you don't have any doubts as of now. So I'll just move to the next one. Right. So the next step is initially we have decided the loads that are coming onto the member, and then we have decided the dimensions of the footings, that is length and width of the footings. Now the next thing that we have to decide is the upward soil pressure. Okay, the next thing that we have to decide is upward soil pressure. So how to decide this upward soil pressure? So upward soil pressure is usually denoted with small w, that equals to small w equals to what is the total load. The total load is 1650 divided by area of the footing provided. What is the area of the footing provided? 5.63. Okay, upward soil pressure, how will you define? The total load coming on to the base of foundation, which is 1650 kilonewtons, that is 1500 plus 150. Here you can see. Okay, 1500 plus 150 will give you 1650. So total load divided by provided area, not the required area. Provided area is this one, required area is this one. So we have to work with the provided area, not with the required area, because this area we are not providing anymore. This was the required area. So how much we have provided? We have increased the dimensions to the nearest round of value, and hence we have got a much greater area. So therefore, larger area means better pressure distribution. So 1650 divided by 5.63 will give you 293.33 kilonewtons per square meter. Kilonewtons per square meter. So this is the upward soil pressure. Okay, this is the upward soil pressure that is coming onto the that is coming at the base of the foundation. So as a result of load coming from the column, okay, as a result of load coming from the column, the reaction force, whichever is acting at the bottom of footing, is known as upward soil pressure. Okay, how to define this upward soil pressure? As a result of load, okay, as a result of load coming from the column, okay, as a result of load coming from the column, the reaction force, okay, the reaction force acts at the bottom of the footing is known as bottom of the footing is known as upward soil pressure. Up pressure. So that's how you can define the upward soil pressure. I hope it is clear what is meant by upward soil pressure. So whatever the load that is coming from the column, that load should exhibit the reaction force. We have discussed that in the very first session. So that reaction force is called as the upward soil pressure. Okay, that reaction force is called as upward soil pressure. And while designing the footings, okay, while designing the footings, we have to design for upward soil pressure only, not for the load coming from the column. Okay, we always have to design the footings, or we always have to design the footings for upward soil pressure, not for the load coming onto the column. This is the most important thing. Okay, so while designing the footings, we have to design for upward soil pressure, not for the load coming onto the column, or not from the load coming from the columns, you can say. Okay, let me write that statement. Just give me a second. While designing footings, it got stuck. Just a second. Yeah. So while designing footings, While designing footings, we have to design for upward soil pressure and not for load coming from the column. That's the condition that we have to remember. So, right. So now one more condition that we have to remember here is upward soil pressure must always be less than, okay, upward soil pressure must always be less than the SBC of a soil. Okay, upward soil pressure must always be less than the SBC of soil. Okay, upward soil pressure must always be less than the SBC of soil. Just a minute. Right. So now what we have to do is we have found out the length of the footing. We have found out the width of the footing. Now the next thing that is pending is the depth of the footing. Okay, the next thing that we have to find out is the depth of the footing. So how to find out the depth of the footing? So that's the next thing. So the next thing is depth of footing. Depth of footing. Correct. So how to find out the depth of the footing? So usually the depth of the footing is dependent on the moment of coming from the soil or the moment of the footing. That is moment along the length direction and moment along the width direction. So apart from the moment, we have two more conditions. So the depth of the footing, okay, the depth of the footing is influenced by, okay, is influenced by two conditions. The first condition is called as flexural criteria. Okay, the first condition is called as flexural criteria, and the second condition is called as shear criteria. These two are very much important, not just in the manual design, even in the software design also. So the depth of the footings is influenced by two conditions. The first one is called as flexural criteria, and the second one is called as shear criteria. So whatever the depth is required as per the flexural criteria, so we'll do the design requirement both for flexural criteria and shear criteria. But what we have to understand from this is whatever the depth is required, okay, whatever the depth is required as per the flexural criteria, okay, as per the flexural criteria, that depth, okay, that depth we will check against, okay, we will check against the shear criteria. Okay, this is vice versa. If you are doing the design for flexural criteria, then you have to consider the same design for shear criteria also. If you are doing the design for shear criteria, then you have to design the same criteria for flexural criteria also. So if it gets safe in shear criteria, okay, if it gets safe in shear criteria also, then only we will finalize the depth of the footing. Okay, then only we will finalize the depth of the footing. So that's how we are going to decide the depth of the footing. So it has to pass through the flexural criteria and it also has to pass through the shear criteria. Only when the depth of the footing is satisfying both flexural criteria and shear criteria, then only we will finalize the depth of the footing. Okay, then only we'll finalize the depth of the footing. Right. So now here we have couple of important things that need to be understood before designing the depth of the depth of the foundation or depth of the footing, you can say. So let me have a simple diagram here. Suppose let me just draw the diagram. Let me call this as the foundation slab. Okay, and then let me have the column also. Let's consider this as the column, which is positioned at the central part. Right. So this is the column and then this is the footing. Now, whenever the load comes from the column, Okay, whatever the load that is coming from the column, suppose if you take this as the load that is coming from the column, let me just give it a couple of others. Yeah. So whatever the load that is coming from the column, this load, okay, this load will be distributed or will be transferred to the foundation slab. Okay, it will be transferred to the foundation slab. But here, one thing which is very important to understand here is, so along which portion of the foundation slab the column is acting. So the column is placed only at this particular portion. Okay, only at this particular length, the column is having the attachment to the base of foundation. But what about the remaining portion? It is a cantilever portion. There is no, actually speaking, there is no load that is coming onto the left and right cantilever portions of the foundation slab. So the most amount of load will go through this portion of the slab, which is called as stiff area. Okay, most portion of the load, whatever that is coming onto the foundation slab from the column, only this blue color portion will experience most amount of load. And this portion is called as stiff area. Okay, this portion is called as stiff area. So why we need to consider this stiff area in the software calculation? This stiff area design is very much important, because if you don't do the design for stiff area, because why it is required to do the design in stiff area, because maximum amount of loads will be experienced by this portion of the foundation slab. Okay, the rest, the right side and the left side of the foundation slab will not experience that much amount of load. Okay, they'll also experience, but not as much as the stiff area. So that's why when you are designing the foundations, okay, when you are designing the foundations, it is important to consider the stiff area. Now here you may have a question. So why the loads will not be here? Loads will be there, but what type of loads? The soil pressure will be there. What type of soil pressure? So you're going to cover this entire area with the soil, right? You're going to pour the soil here. So the cantilever portions, whichever that are there, it will experience the soil pressure that is coming from the top. Now, you might have a question, why we are considering only the stiff area as most important one? Why not these cantilever portions, even though they are experiencing loads? It is because whatever the load that is coming from the column into the stiff area is much, much larger than the soil pressure that is acting on the cantilever portions of the foundation slab. Okay, the cantilever portions will also experience pressure, but that pressure will be very small than when you compare with the stiff area. If you don't design the foundation, okay, if you don't design the foundation for stiff area, what will happen is the foundation will experience the uplift condition. Okay, the foundation will experience the uplift condition. What is that uplift condition? So the foundation will experience something like this. Okay, it will experience the uplift condition. So here, this portion of the foundation will be uplifted, and this portion of the foundation slab will also get uplifted. So this is how it will become. Okay, this is how the uplifting will happen. So to avoid this uplifting portion, okay, to avoid this uplifting portion, we have to design the foundation. We have to design the stiff portion of the slab for a greater depth and also for criteria related to shear and flexure. Okay, criteria related to shear and flexure. So that's why we have to focus very much on designing the foundation for stiff area, especially when you are deciding the depth of the foundation. Okay, especially when you are deciding the depth of the foundation. Right. So now let us work on that. So how to decide the depth required against, let me call this as a 5.1 depth required, depth required against the flexure. The depth required against the flexure. Usually we'll design it for flexure and then we'll check it for shear criteria also. I'll show you how to check it for shear criteria. So here we have to calculate the moment. Flexure is nothing but moment, bending force. So we have to calculate the moment at the face of the column. Okay, at the face of the column, along the length and along the width of the footing. Let me have this diagram first. Right. So if you see this particular diagram, let me copy this diagram here. Right. So if you see this particular diagram here, we have to decide Let me delete this all things. It's not required. Right. So the depth required against the flexure is calculated based on the criteria which is called as flexure criteria. Okay, based on the flexure criteria. Now here we have to calculate the moment at the face of the column. So whatever is the face of the column along the width side and also along the length side. This is the length side and this is the width side. So along the faces of the columns, that is along A and along B, small a and small b. Those are the faces of the column. So we have to calculate the moment at the face of the columns on the length direction and also on the width direction as well. Okay, length and width direction as well. Before that, what we have to do is we have to calculate the projected length along the length and width. So what is this projected length or projected span? So if you take along the length, okay, projected span or projected length along length direction of the footing equals to L minus A divided by 2. So we have to find out this length. Okay, we have to find out this length. Yeah, sorry, there was some internet connection issue. Let me just share the screen and then I'll start. Right. Can somebody please confirm me? Are you able to see the screen?
Yes, sir.
Yeah, fine. Thank you. Right. So now what we have to do is before we calculate the flexure criteria, we have to calculate this projected length. So first let us calculate the projected length along the length direction or along the length of the footing. So how will you find out along the length of the footing? The total length of the footing is taken as L minus the side of the column. The longer side of the column is A, L minus A divided by 2. So half of this one. So therefore, you are going to get this projected span along the length direction. And along the width direction, the total width of the footing is capital B and the width of the foundation, width of the column is small b, that is capital B minus small b divided by 2. So therefore, you are going to get the width or the projected span along the width direction. So the projected span along the width direction equals to b minus b by 2 and the projected span along the length direction equals to a l minus a by 2. So let me call that as projected span along length direction equals to L minus A by 2, capital L minus A divided by 2. So what is the total length of the footing? The total length of the footing is 2.5 meters. Okay, this one. So the length of the footing is 2.5 meters and width of the footing is 2.25 meters. So length of the footing equals to 2.5 meters minus what is the longer side of the column? 450 mm. That is 0.45 divided by 2. Therefore, you're going to get the value as 1.025 meters. This is projected span along length. Similarly, we have to calculate projected span along width as well. Okay, projected span along width as well. That equals to capital B minus B divided by 2. So what is capital B? Capital B is the width of the foundation. What is width of the foundation? It is 2.25 meters minus what is the width of the column? The width of the column is 0.23. That is 230 mm. So I'll just make it as 0.23 divided by 2. So that equals to 1.01 meters. So that's how you have to calculate the projected span along the length direction and projected span along the width direction. Right. Based on this, we are going to find out the moment along length direction and the moment along the width direction. Without calculating the projected spans, it is not possible to calculate the moment values. Okay, it is not possible to calculate the moment values. Let us check how to do that. So moment along length, I'll just make it as m suffix l. Okay, moment along length direction equals to, let me call, yeah. So moment along length direction equals to, so how to do that? So upward soil pressure. So the formula is soil pressure, upward soil pressure into width of the foundation. Okay, width of footing or foundation, you can say width of the footing into projected span, okay, projected span along which direction? We are finding out the moment along length direction. So therefore projected span along length, projected span along length whole square. So projected span square divided by 2. So this is how you're going to find out the moment along a particular dimension, either it is length direction and width direction. So here, one thing which we have to understand is when you are finding out the moment along the length direction, you need to consider the width of the footing. When you are finding out the moment along the width direction, you have to consider the length of the footing. That is the most important thing. Okay. When you are finding out moment along length direction, we have to consider the width of the footing. When you are finding out moment along width direction, you have to consider the length of the footing. It's a vice versa condition. If you are finding out X, you have to consider Y. If you are finding out Y, you have to consider X. That way you can say. So therefore, moment along X direction or moment along length direction. What is the upward soil pressure? It is something like 293 something. Yeah. So 293.33. Okay, 293.33. That is the upward soil pressure into what is the width of the foundation? 2.25. Remember, that's the width of the foundation, not the length. Okay, width of the foundation or width of the footing into projected span. What is projected span along length? It is 1.025 meters. So 1.025 square, okay, divided by 2. So that's how you have to find out the moment along the length direction. Okay, moment along length direction. So if you solve this one, you're going to get the moment along length direction as 346.07 kilonewtons meter. So this is the moment along length direction. Similarly, we have to calculate the moment along width direction as well. Okay, but before finding out moment along width direction, let us find out the factored moment also. Along the length direction, let us find out the factored moment. So how will you find out the factored moment? I'm just calling it as MLU. U represents ultimate moment. So factored moment equals to 1.5 times of 1.5 is the factor of safety into 346.07. That's the moment along length direction. So when you solve this one, you're going to get the value as 520.05 kilonewton meter. Okay, 520.05 kilonewton meter. So this, for this moment, we have to decide the depth of the foundation. That is along length. Now let us find out the same thing along width also. Okay, let us find out the same thing along width direction also. So the moment along width direction, okay, moment along width, I'm calling it as MB. Okay, moment along width, I'm calling it as MB. Same formula, upward soil pressure into, here when you are calculating the moment along width, you have to consider the length of the footing, okay, into length of the footing into projected span along width. Okay, projected span along width whole square divided by 2. So how to find out this value? MB equals to, we know the upward soil pressure, which is 293.33. Okay, let me write that 293.33 into the length of the footing is 2.5 into the projected span along the width is 1.01. Okay, I'll just make it as 1.01 square divided by 2. So this is how you can find out the moment along the width direction. So therefore, the value will become 374.03 kilonewton meter. Okay, 374.03 kilonewton meter. Let us find out the ultimate moment also. MBU equals to, so how to find out MBU, that is ultimate moment along the width direction, that equals to 1.5 times of 374. Okay, 374.03 equals to 561.05 kilonewton meter. So from this, we have got the length along moment along the width direction and moment along the length direction. So these things we have to remember. Okay, I'll just make it in bold. Right. So that's how we got the moment value. So now what we have to do, we have to find out the depth. That's our ultimate intention. So here, the depth value, okay, the depth value that the of depth of the footing depends on grade of steel. It depends on grade of steel. So how it depends? You have the formula which is mu limit or limiting moment of resistance. In design of concrete structures, you must have studied. So I'll not go into the details of that one. But for Fe415 grade of steel, in our case, it is Fe415 grade of steel. So for Fe415 grade of steel, the limiting moment of resistance is 0.138 FCK dd square. That's the formula. Let me keep it in a better way. 0.138 FCK BD square. This is the formula when you are designing it for Fe415 grade of steel. Okay, for Fe415 grade of steel. So this is the formula to find out the limiting moment of resistance. Now here we have the value of mu and we also know the FCK, which is grade of concrete. B is something which we have to be very careful about. Right. So now here we got two mu values, that is moment along length direction and moment along width direction. So which one we have to consider while calculating the value of D, that is depth of the foundation. So the moment is taken as the largest of MLU and MBU. Okay, whichever is the largest value, that will be your maximum moment. Okay, when you design the things for maximum conditions, then the safety will be very good. So mu is actually, okay, mu is the largest of MLU and MBU. Okay, mu is the largest of MLU and MBU. So what is the value of mu now? The value of mu will be 561. Okay, therefore, let me think this way. Yeah. So therefore, mu equals to 561 561.05 kilonewton meter. Okay, 561.05 kilonewton meter. Right. So now from this we have to calculate. Now, what is the value of mu? It is actually the moment along the width direction. Now here the value of B, okay, the value of B is also taken in such a way that whichever side you are considering the highest moment, that side length or that side dimension you have to consider. Let me tell you that. So the value of mu is fixed, which is 561.05 into 10 power 6. I am just converting into Newton mm. So 561.05 into 10 power 6 equals to 0.138, okay, into FCK, that is grade of concrete is 20, into B. So along which side we are considering the value ultimate moment? It is along the width direction. what is the length or what is the dimension along width direction? The dimension along width direction is 2.5 meters. That's the dimension of the footing. Okay, 2.5 meters. So 2.5 is nothing but 2500. So that's how you're going to get the value of B into D square. We don't know the value of depth. So I'm just making it as D square. So when you solve this one, you're going to get the value of D as depth of the footing. Okay, depth of the footing. D equals to, now this is not the overall depth, this is just the depth of the footing. So 285.15 mm. So this is the value that you will get. Okay. Now here the question is, this is the depth which is based on flexural criteria. Okay, this is the depth which is based on flexural criteria. Why I am calling it as flexural criteria? Because we have decided the depth based on moment conditions. Moment is nothing but flexure only. So we have decided the depth based on flexural conditions. But in actual case, the depth is influenced by shear criteria, not for flexure criteria. Okay, in actual scenarios or in real time scenarios, you can say, in actual cases, the depth is influenced by, okay, the depth is influenced by shear criteria. Okay, the depth is influenced by shear criteria. So therefore, okay, therefore we will increase the overall depth. Okay, we will increase the overall depth to, let's say I will increase it to 650 mm. Now you might have a direct question one here. So the depth of the footing, let us consider this as the effective depth, small d. So the depth of the footing is 285 mm, but I am considering the overall depth, that is capital D, as 650 mm directly. Why I am not rounding it off to either 290 mm or 300 mm? If you round it off to the nearest possible value or nearest 10-digit number, let's say some 300 mm. Now it will be safe in flexure criteria, but it will never be safe in shear criteria. That you will understand, especially when you are designing it in the Excel sheet validation. In tomorrow's session, I'll show you how to validate the same result in Excel sheet also. Then you will understand this depth. But for time being, just remember that I'm increasing the overall depth to 650 mm. Now you might have a question here. Why only 650? You can I go with 600? Yes, it is possible. We can go. We can go for 500 also, 550 also. But what happens when you don't go for higher depths? That condition I'll show it in the Excel sheet validation in the next session. Okay, but for time being, just remember this one. I'm just increasing the overall depth of the footing as 650 mm. So this is basically the capital D value. Capital D equals to 650 mm, the overall depth of the footing. Okay, the overall depth of the footing. Suppose if you found or if you find 650 mm to be oversafe. Okay, when we'll do it for the shear criteria, when we are calculating it for the shear criteria, or when we are calculating it for one-way shear and two-way shear, if we found this 650 mm as over depth, then we will decrease the depth. If we find this 650 mm as not safe, then we have to increase the depth. If we find this 650 mm as the sufficient one, then we don't change anything with this. Okay, that's the condition here. So here I'm just assuming some value, but in the next session, I'll show you very good in an Excel sheet, because in Excel sheet, I have the validation values. So I'll show you that in the Excel sheet. For time being, let us just assume that the overall depth of the foundation as 650 mm. So from this, we can calculate the effective depth. Okay, effective depth small d equals to overall depth, that is 650 mm, minus cover. Okay, let me write it in this way. Overall depth, that is capital D, minus clear cover. Okay, minus clear cover. Let me call this clear cover as D dash. Okay, let me call this as D dash, minus diameter of bar divided by 2. Okay, diameter of bar divided by 2. So here, usually when you are designing the foundations or when you are designing the footings, the diameter of bar is taken as 16 mm diameter. Okay, assume 16 mm diameter of bars. Okay, so therefore the effective depth small d equals to, okay, the effective depth small d equals to overall depth is 650 mm minus clear cover. For footings, the clear cover is taken as 50 mm minus 16 by 2, which will become 8. So therefore the effective depth will become 592 mm. Okay, the effective depth will become 592 mm. So with this, we have found out the length of the foundation, width of the foundation or footing, and depth of the foundation. So let me write that length of the footing equals to 2.5 meters and width of the footing equals to 2.25 meters, and the overall depth of the foundation equals to 6.5 meters. So we have to finalize the length, width, and depth of the footings. Okay, length, width, and depth of the footings. So in the next class, what we are going to do is we are going to calculate, okay, we are going to calculate the reinforcement requirements. Once we calculate the reinforcement requirements, then we will calculate the one-way shear and two-way shear, and then we will check whether this 650 depth is safe in shear criteria also or not. If it is not safe in shear criteria, then we have to increase. If it is over safe, then we have to reduce by a little. If it is exactly same, then we don't need to change any of this overall. That we'll see it in the next session. Once we do the shear criteria check, that is one-way shear and two-way shear criteria check, then you'll understand that. Right. So that's from my end for this particular session. If you have any doubts so far, you can unmute and let me know. Thank you.